Next exercise 5. Here we have the ring Zn and we are being asked to show that any non-zero element in this ring is either a unit or a zero divisor. So let's see the solution. Let's start off by taking a non-zero element. PA non-zero element. Now two cases arise. Either k is relatively prime to n or it is not relatively prime to n. So let's the relatively prime to n case first. First assume that k is relatively prime to n. That is, their greatest common divisor is 1. Then we know that Ka plus Nb is equal to 1 for some integers a and b. We know that the GCD of any two integers, when it exists, can be expressed as a linear combination of the integers with the coefficients also integers. So here the GCD is 1, so 1 can be expressed as a linear combination of k and n with these integer coefficients a and b. Then in this ring, this equation leads us to this, because in this ring Nb is equivalent to 0, so Ka is equal to 1, hence K times A mod n is also equal to 1, because we are in this ring Zn, so addition and multiplication have their modulo n versions. So you can replace any integer by its remainder when you divide that integer by n, and in fact that's what we are considering. When we say a, we actually mean a mod n, and anyway in Zn, a and a mod n are the same thing, where a mod n belongs to Zn. Thus K is a unit. Now next we consider the case where this GCD is not 1, it is something, an integer greater than 1. Next assume that the GCD of k and n, say we call it d, this is greater than 1. Okay. Okay, because the GCD is d, so d is the greatest common divisor of k and n. So that means d divides k. So k will be a multiple of d. Then k will be equal to, say, Sd for some integer s. Now, just like k is a multiple of d, n is also a multiple of d. And in fact, because d is greater than 1, n divided by d is less than n. It's a positive integer less than n. And that means what? Because n divided by d is a positive integer less than n by d is not divisible by n. In other words, n by d in Zn is a non-zero element. Now, n by d, in fact, let's just write all these things. Since d is greater than 1, this is a positive integer less than n. Thus, n does not divide n divided by d, i.e. this is non-zero in our ring. Okay. Now, what happens if we take the product of this non-zero k and this non-zero n divided by d? This is equal to k divided by d times n. Now, k divided by d is some integer s times n. Now, this is a multiple of an integer multiple of n. So, in Zn or Zn, this thing is equal to 0. So, although these elements k and n divided by d are non-zero elements in Z and their product is 0. So, now k is a zero divisor. Hence, k is a zero divisor. So, that arbitrary non-zero element k is either a unit or a zero divisor, and that's what we wanted to show. Next, exercise 6. Find a non-zero element in a ring that is neither a zero divisor nor a unit. So, in this exercise we have seen that this modulo n rings, n of course you can change, so you will get infinitely many such rings. In them, non-zero elements are classified into these two categories, the zero divisors and units. But in general rings, that is not necessary. we can have a non-zero element which is neither a zero divisor nor a unit, and we can pretty easily get this example in our most familiar ring, the ring of integers. In the ring of integers, the element say 2 is neither a zero divisor nor a unit. We know that in this ring only two elements are units, that is, they have multiplicative inverses. One of them is the integer 1 and the other one is -1, and each one of them is an inverse of itself. The other elements, other integers don't have inverses. So for example 2 is not a unit because it does not have a multiplicative inverse, but at the same time 2, in spite of being non-zero, is not a zero divisor also. You cannot multiply 2 and a non-zero integer and get 0. That will never happen. This ring is an integral domain. So this is one such example of an element in a ring which is neither a zero divisor nor a unit. Next, let R be a finite commutative ring. With unity, there is a multiplicative identity also. Prove that every non-zero element of R again is either a zero divisor or a unit. So not just the rings Zn or Cn. In general, any finite commutative ring with a unit element must be like this. So the Zn's in particular are also finite and commutative and they have unit element. So this is more general than that. And in this type of rings also that same thing happens. Now what happens if we drop the finite condition? Then this property will be lost. Okay. So here again, just like before, we are going to start by considering a non-zero element. Let S belonging to R be a non-zero element. Now what we do, we consider this set S whose elements look like this, SR, where R is any element in our ring. Now as you can clearly see that this capital S is a subset of capital R. Now as a subset, this S may either be equal to R or it may be a proper subset, but whatever the case is, note that because S is a subset of R and R is finite, so S is also finite. Now if it happens that S is equal to R, then since 1 belongs to R, 1 is the unity in R, we have 1 equal to SR for some particular R from the ring. So in this case, S is a unit because R will now be a multiplicative inverse of S. If on the other hand S is not equal to R, then because S is a subset of R, S will be a proper subset of R. Then S has fewer elements than R, and it makes sense to say that because the sets we are dealing with are finite, so fewer elements, that thing makes sense. Okay, now look at the structure of the elements of S. The elements of S look like this. Say if your original R is this, R1, R2, R3, Rn, this is your original R. S looks like this: SR1, SR2, SRn. S consists of all the multiples of small s by ring elements. Now if this must have fewer elements than this, then there should be some repetition in this list. There should be some collapse, that is some SRI should be equal to some SRJ. Naturally, because in that way only the number of elements in S will be fewer than what we have here. So that is why Hence, there exist distinct elements R1 and R2 belonging to R such that SR1 is equal to SR2, some repetition, but then SR1 using elementary ring properties, we have this, where because R1 and R2 are distinct, their difference is a non-zero ring element. So we have been able to show that there is a non-zero element in the ring such that if you multiply that with S, you get 0. So that means S now is a zero divisor. Thus, S is a zero divisor. Now, if we drop the finite condition on R, then we can again take the ring of integers, and where we have already seen that this property is not there. So we write in the ring of integers two is neither a zero divisor nor a unit. Note that the ring of integers is almost like what we have here. I mean, in the hypothesis, a commutative ring with unity, but the only thing is that it is not finite, it's an infinite ring. So there the hypothesis is not true and the conclusion is also not true. Next, let A not equal to 0 belong to a commutative ring. Prove that A is a zero divisor if and only if there exists or if and only if A square B is equal to 0 for some B not equal to 0 in the ring. So So it's a double implication. If this happens, then A is a zero divisor, and conversely also. So let us first consider this. Assume first that the ring has an element P not equal to 0 for which A square B is equal to 0. We have to prove that A is a zero divisor. Now two cases will arise. If AB is equal to 0, AB may or may not be 0. If AB is 0, then automatically A is a zero divisor, because we have found a non-zero element B such that if we take the product of A and B, then we get 0. Then by definition A is a zero divisor. On the other hand, if AB is not equal to 0, then A times AB is equal to A square B is equal to 0. Now the non-zero element by which if we multiply A, we get 0, that role now is played by AB instead of B, because now AB is non-zero. So in this case also, A is a zero divisor. So one half of the claim has been established. Conversely, assume that A is a zero divisor. Then by definition there exists an element in order to, you can, if you want, you can take B also, but in order to distinguish this B from that B, let me write B prime. There exists a non-zero element B prime such that in the ring, of course, A B prime is equal to 0. But then A square B prime, which is A B prime, is also equal to 0, and that's it. We had to show that there is a non-zero element such that A square times that element is 0. So this completes the solution. let us solve another one. Exercise 9. Find elements A, B and C where in the ring in this ring. Direct sum of 3 copies of the ring of integers such that AB, AC and BC are 0 divisors. But ABC is not a 0 divisor. Okay. Actually, this is an odd numbered exercise, right? And odd numbered exercises have their solutions or at least hints of solutions at the end of the text. So the author himself has taken these particular elements. Consider A equal to this ordered triple 1, 1, 0, B is this and C is this. Okay, so it is left to you to verify that the claim of this exercise is true for this choice, these choices of A, B and C. So with this I am ending this video. We will solve more exercises from this set of exercises in the next Gallian upload on rings. And tomorrow is Sunday, so tomorrow we again have analysis. So that will be all for tonight. If you want to say something about these things, if you want to make remarks, you please write in the comment section below, or you can mail me at my usual address. The link will be there in the description. So with that, I am signing off. This is me, Lucifer, from A Mathematical Room. Have a nice night.